Hi, my name is Molly Payne, and I am a Fisheries Sciences Master's student at the University of Alaska Fairbanks, and I'm advised by Dr. Peter Wesley. Today, I'm going to talk about what makes streams attractive to stray hatchery chum salmon in southeast Alaska. And if you're going to talk about straying, or more broadly, population dynamics in salmon, you have to talk about metapopulations. This is because metapopulation dynamics enable the persistence of healthy wild salmon populations. And this relates, actually, to straying in hatchery salmon, which I'll get into more in just a bit. A metapopulation is a group of populations that occupy spatially separate habitat patches. So for salmon, this is populations living in different streams, as salmon do. They achieve this by homing, which is where they return to the same stream in which they were born. This provides many advantages for the whole metapopulation, perhaps the most important of which being local adaptation. This is where salmon become adapted to the unique conditions of their stream, whether it be cold temperatures or heavier bear predation, etc. They do this by spawning there generation after generation, and they become so good at it that they actually have really high reproductive success at those sites compared to if they were to spawn somewhere else. For this to be a metapopulation, though, you also have to have connection or movement of individuals between the populations. So this occurs via dispersal, which we refer to as straying for salmon. This is where adult salmon return to a stream other than the one in which they were born to spawn. This also provides important benefits for the metapopulation as well. For example, gene flow between otherwise completely reproductively isolated populations, as well as the ability to colonize available habitat from other populations. In a nutshell, a salmon metapopulation, you can think of it as a well-oiled machine, driven by a dynamic balance between homing and straying. It really is fundamental. It's what has enabled salmon's success and persistence throughout time in the face of environmental variability. Since straying is a natural part of this process, that means it's only natural for hatchery salmon to stray in some proportion as well. And this can actually have some negative consequences, certainly for wild salmon for many reasons that I don't have time to go into right now, but ask at the end if you are interested. But from a management perspective, this can cause incorrect population assessments. So it's actually hard, or I would probably even say impossible, to tell the difference between hatchery and wild salmon from an aerial or foot survey. And so you might say, well, there's 1,000 salmon in this stream, that's a healthy population, when in reality, half of them are hatchery salmon, and the wild population is in rapid decline. That's a serious accounting problem, and that can foil your ability to really accurately manage and protect a wild spawning population. So the logical next question to me then is, well, okay, how can we make the hatchery salmon stop doing that, right? And I would say, for one, we could try and identify influential factors. What factors influence or even serve to increase the rate of straying of hatchery salmon? From the literature, there are already a few things that we understand relatively well, genetic origin of the hatchery fish being one. So if you take all of your hatchery fish from one river, those fish are more likely to stray back to that river compared to other sites as adults. Another one is if you interrupt their olfactory development as juveniles, that makes it harder for them to smell their way home as adults. These are demographic factors, which answer the question of what is it about the fish themselves that influences or even increases the rate of straying. What we actually don't have as much knowledge about is what about the end location where these strays are ending up. Is there something about those places that is actually attractive to hatchery salmon and might influence or increase the rate of straying? And actually there is emerging evidence of this. Take this example from Little Togiak Lake on the Wood River system. This study looked at adult sockeye salmon returning to two creeks, C Creek, which had more woody debris and less bear predation, versus A Creek, which was narrower, had less vegetative cover, and more bear predation. Take a moment and ask yourself, if I were a salmon, which stream would I rather go to? Well, if you guessed C Creek, you were right. They found that 50 strays from A Creek showed up at C Creek, whereas virtually none ended up straying to A Creek. What this tells me is that salmon are actually comparing site quality between different streams and using this to make an informed decision about where they want to spawn, right? They want to pick the place where they're going to have the highest reproductive success. So that leads to my question of my project, actually, which is what stream characteristics make streams attractive to hatchery salmon strays, right? Can I apply that example I just talked about to Southeast Alaska chum salmon? With my hypothesis, being that yes, I can. I can predict stream attractiveness by analyzing stream characteristics. So to situate this study, I'm using data on chum salmon, hatchery chum salmon in Southeast Alaska. There are a series of enhancement hatcheries in the region, and by enhancement, that means that those fish are intended to enhance the fishery. They are not intended at all to end up on stream spawning grounds with wild salmon, right? There should be literally 0 hatchery salmon on stream spawning grounds in the wild. There is concern, though, that this is actually not the case, right? And so the Alaska Hatchery Research Project was designed to actually go out and sample streams and see, are there hatchery salmon spawning on these streams, and what impact might that be having on wild salmon populations? So that is actually an awesome data set available for me to use. So I have data of the counts of hatchery salmon spawning on 59 streams throughout Southeast Alaska over a 10-year period. And these fish originated from a series of approximately 10 different hatcheries depending on the year. So I decided to take that information and actually fit a model with it to see, can I find or identify some covariates to predict the number of strays showing up at these streams. So I fit a generalized linear model with number of strays from the Alaska Hatchery Research Project as my response variable. So then what covariates did I end up picking? Well, the first and most important one to my mind was distance from the nearest hatchery. And here's why. This graph shows the proportion of hatchery origin spawners in a stream on the y-axis as a function of distance from the nearest hatchery release site on the x-axis. And you can see that there's actually a bit of a threshold here. It's about 25 or 30 kilometers. You have higher on average stray rates, in some cases insanely high, upwards of 80 or 90%. But outside of that threshold, right, you can't really predict high stray rates anymore. So you could have a stray rate of, 6 or 7% here at 45 kilometers from release, or at, 120 kilometers from release site. So distance is really important for predicting a high number of strays within a short distance. But outside of that, you actually needed other covariates in the model. So briefly, also, I added an additional layer of the distance prediction, which is also the number of fish released within 40 kilometers, with the prediction being that if you release more fish close to a release site, you're going to have more strays. Conspecific abundance refers to the size of the wild population. So I have 2 competing hypotheses for that one. One is that if you have a really large wild salmon population, wild chum salmon population in that stream, that's going to indicate attractiveness. That means that's good habitat because a large population was able to maintain itself there. And that also means mating opportunities for a potential hatchery stray. Alternatively, a stream with a small wild population might also be attractive because that means less competition for mates and resources in that stream. Similarly, pink salmon occupy a lot of the same streams as chum salmon in Southeast Alaska, and I looked at that through a similar lens, right? A lot of pink salmon in a stream means it's good habitat, right? A huge pink salmon population is able to thrive there. But alternatively, that might also be unattractive because that means it's going to be really crowded and you're going to have to compete really hard to get space to spawn. So that could go either way as well. And finally, the coefficient of variation of stream flow. This is based on studies I've read talking about stream flashiness or stream flow variation actually being a really important cue to stimulate upstream movement of migratory salmon. And then I also looked at a number of other predictors, which surprisingly ended up contributing nothing to the model. I found that the model did shockingly well for how messy the data set was. It accurately predicted 55 out of 59 streams to be either attractive, unattractive, or somewhere in the middle. And here's the information that went into that. So as predicted, distance from the nearest hatchery was negatively correlated with increasing strays, meaning if you're further from a hatchery, further from a source of fish, right, fewer strays. Similarly, if you release a large number of fish near a stream within 40 kilometers, you're going to have increasing strays, as shown by the blue increasing positive relationship. Chum salmon abundance kind of surprised me. That was negatively correlated, which would suggest the competition effect, whereby a smaller population of wild chum salmon would be more attractive, because that would mean, to my interpretation, less competition for stream resources. Pink salmon abundance was actually a quadratic relationship, which I think would be easier to show you. The way that I interpreted this was at low abundances of pink salmon, that's a sign of bad habitat, right? A pink salmon population failed to establish there, so that's not a good place to spawn for whatever reason. Conversely, if there are too many pink salmon there, that stream is going to be so overcrowded, it's going to be a constant struggle to even find space to spawn. So there's going to be a sweet spot in the middle of stream attractiveness related to pink salmon abundance. And finally, CV river discharge, stream flashiness, you could also call it, very strongly positively correlated with the number of strays. So here's that effect visualized on its own figure. You can see pretty small error around it, especially at lower values. And again, this is just a sign that flow variability, is such an important cue, particularly as flows start to drop after a big rainstorm. That tells fish, right, here's a river, like the river's right here, come up, there's habitat available for you. So, can we predict stream attractiveness using stream characteristics? Yes, I think we probably can, right? In particular, using coefficient of variation of river discharge, number of fish released near that stream, and pink salmon abundance, interestingly. The broader impact of this study is actually, hopefully, that I can use this information as a management tool. I still need to work out the details of this a bit more, but something like saying, here's an attractive stream, here's a radius of where you should not put a release site if you don't want a ton of those hatchery fish to stray to that stream when they return as adults, right? So, as a way to reduce straying, to help with population assessments, to have more fish ending up in the fishery and not in streams, and also to protect wild salmon populations. Thank you to many people. I'll end it there so I have time for questions.